So let's see. These are the two things really. One is stress and the other is strain. So stress we saw was there were two types of stresses really. There was a normal stress which we called sigma, and then there was there was the shear stress that we call tau. And the difference between the two was that sigma was defined as n over a, n was the normal force, a was the perpendicular area, and tau was defined as v over a, whereas v was the shear force which was parallel to the cross-sectional area. Those were the two basic definitions we did. Now, similarly, strain is also, there are two types of strain. The first one is called the normal strain, and the second one is called the shear strain. Let me start by giving you the two formulas. So we go with strain and how do we define strain? Before I even talk about the formulas, I think I need to talk about what does strain signify. So remember, the stress was signifying a kind of a force per unit area. It was, you were taking the load and dividing it by the area. You were dividing, or you were kind of normalizing the load using the area on which that load was acting. Let me admit these people. There we go. So, like I was saying, stress was basically the load normalized over the area. Now, strain is something different. Strain talks about the geometrical change caused by a load acting on a member. So, for example, if you had a member, let's say something like this was your structural member, and you applied a load P on it like this. The length of the member, let's say, was L. Then if this load P is applied on this, question to you, will there be any stress in this member? Yes or no?
Yes.
Yes, there will be a stress. And we define that it will be the normal stress given by P divided by the cross-sectional area. That's how we define the stress. Now, when we talk of strain, we say that when this force acts on this member, the length of the member is going to change also. Let's say this is the new length. The length may be increasing on both sides, but let's say I'm showing the entire length increase on one side. So let's call this as delta L. Due to the application of the same force, I find the geometry of the member has changed. Its length was L, now it has become L plus delta L. This change of geometry is accounted for by strain. And so this kind of strain in which there is this is called the normal strain. This is the first kind. Just like we had normal stress and shear stress, similarly we have normal strain. This is the normal strain I've just showed you. It is represented by the Greek letter epsilon. Epsilon is defined as the change in length over the original length. So if delta L was the change in length caused by this force, then L was the original length, then epsilon or the normal strain will be defined as delta L over L. Everybody good? This is the first definition, the normal strain. And then there is the other kind which is called the shear strain. And this actually deals a little bit with the geometry. So, for example, if you had a member something like this, let's say I have a sheet a metal sheet, something like this, and there was a shear force acting like that. So you know that shear is normally parallel to the area. So there is a shear force acting on this. And if that be the case, let's say your this end was fixed. Now, when this shear force acts, what will be the new position of the member? The member is going to deform in this direction. So it might become something like this. You see what I'm saying? So the change in angle here, this angle, this is defined as the shear strain. And shear strain is represented by the Greek letter gamma. Gamma is defined as this angle theta. And the way the book defines it is he doesn't call this angle theta because this is the shear strain, which we're calling gamma. So theta is defining this angle, and therefore gamma will be equal to pi over 2 minus theta. This angle you can say is gamma or the shear strain. So the more the shear strain, the larger is that angle, or vice versa. The larger is that angle, the more is the shear strain. And the less is the shear strain, it means your member can resist shear better. So these are the two kinds of strains: normal strain, shear strain. Now, how about units of strain? Remember, units of stress were what? Pascals, those newtons per meter square. Let's check the units of strain. What will be the unit of normal strain? How do you measure delta L in SI units? It will be in meters. How do you measure your length? Also meters. So, according to our convention, it cancels out. But the tradition or the convention is that you still use the same unit. So you will say epsilon is equal to so many meters per meter or millimeters per millimeter. You don't cancel them out, you kind of speak them out or write them out. So units of strain are normal strain would be millimeters per millimeter, inches per inches, or meters per meter. Normally it's not counted in meters. It's such a small quantity. It's usually in either millimeters per millimeter or inches per inches. So I will say units of strain, normal strain, let's say. Are inch per inch or millimeter per millimeter. But technically, I can also say that it is a unitless quantities. Do you agree? Because the units cancel out. So technically, it doesn't have any units, but in practical life, industry uses the same units, inch per inch or millimeter per millimeter. And I'd like you to be using these also. This could be a concept proportion question. What are the units of normal strain? You will have to say these are inch per inch. Everybody good? How about units of shear strain? What will be the units of shear strain? So obviously, since this is an angle, it will be the units of shear strain would be radians. And radian itself doesn't have any units as such. It's just the measure of the angle, but to say that radian is considered to be unitless also. So it doesn't have any units.
For the units for normal stress, did you say inch per inch?
Correct.
Wouldn't that mean it's without units as well then?
Yeah, that's what I'm saying. You got it right, exactly.
Okay.
So it doesn't have any units. It's a unitless quantity. However, by convention, the units are repeated as inch per inch or millimeter per millimeter. It probably just signifies also which system you are in. So if you say epsilon is, for example, 0.001 inch per inch, you know that you are talking in British engineering system. And if it said the epsilon was 0.0005 millimeter per millimeter, you would know you're talking in SI units. But that's not the reason. That it's just a convention that we still say, we still repeat the units, although they cancel out. Any other question or comment? Well, these are all the definitions you had to know. And I'd like you to remember the 4 basic formulas, meaning 2 for stress and 2 for strain. What are the 2 basic formulas for stress? Normal stress sigma is N over A. Shear stress tau is V over A. And then there was single shear, double shear also we talked about while talking about shear stresses. Then when you come down to strain, then there are another 2 formulas. The normal strain, delta L over L, the shear strain is pi over 2 minus theta. These 4 formulas you should know on, you shouldn't have to consult the equation sheet to know these formulas. These will be your bread and butter for this course. You should know them all the time. All right, let's then just start solving problems. I guess that's all there is in this to explain, and I can go over my PowerPoint also to make sure I haven't missed out on anything. The concept of strain is developed to describe the deformation of a body by changes in length of line segments or changes in the angles between them. That's what you just saw. So epsilon and gamma. And the next thing I'm saying there is normal strain results when normal stress causes change in size. So I gave you the example. You had the member, you had the axial force acting on it. It causes normal stress, all right, but it also causes an elongation, or if it was a compressive force, it will cause a contraction. So it will be positive. What is the extension? If it is increase in length, it is called positive. If it is decrease in length, contraction, it is called a negative strain, normal strain. And then shear strain, we are saying results when shear stress causes change in shape. It quantifies angular distortion. The formulas are as follows, and here is an example for you. If you see this little rod on which we have a force applied at one end and pin joint on the other, also a cable supporting it. Now when you apply the load P, what do you think will happen to the point C? C is going to move down. And how much down will it move will depend upon the strain that this cord BD can take. So BD is going to extend. There will be an elongation in BD. You see what I'm saying? B will take a position somewhere here, B prime. And this rod AC will take the position like this, something at an angle now. And that will cause a strain in the cord BD because its length is going to increase due to this application of force. So that increase in length divided by the original length 300 millimeter will be the strain in this BD. That's the concept of normal strain. And I think I have that other picture also in which the strain is shown in BD. It is BB prime, which is the change in length, and strain would be BB prime divided by BD, the original length, not B prime D, but the original length, BD. So epsilon is defined as delta L over L. So delta L is so much, original length is so much, that is how you define epsilon. And again, units of strain in this case would be millimeters over millimeter. That's how you define it. The final length minus the original length divided by the original length. please remember it like this. And this automatically give you a positive or a negative, because if the final length is smaller, that means there is a contraction or you had a compressive force, then this will come out to be negative. And negative means your size has reduced. Although the sign is positive, negative is not very clearly used in epsilon, but just to remind you that positive, when you get a positive change, it's considered, strain is increase in length, and when it is negative, it is decrease in length.
So I have a question, Professor. During the quizzes or the tests themselves, do you want us to clearly mark whether we believe that the member is in C for compression, or wow, I just went blank. The opposite of compression.
Tension.
Thank you. So do you want us to clearly mark it, or would you understand what our answers are dependent on if it's a positive or a negative value?
Well, what I expect you to be showing me is your epsilon positive or negative? And from there, I will automatically understand if you're showing it positive, it means it's an increase in length. If it is negative, it means it is a decrease in length. That I expect you to be giving me, whether your epsilon is coming out positive or negative.
Thank you.
All right. Any other questions or comments, anybody? So let's move on. Here's the definition of shear strain, and this is the same example I gave you. You had a member like this with one side fixed, AD cannot move. If you apply a shear load there, this is the new position the member will take. And when it takes this position, then what is shear? Theta is not the shear. The shear strain is defined by this change in angle gamma. So gamma is defined as pi over 2, which was the original angle, minus theta, which is the new angle. And the units of shear strain are radians. Let's do an example problem. By the way, your homework one is due tonight. So, and homework one is out of chapter 1, all the sections of chapter 1 stresses. And what we are going to do today, strain, your homework 2 is based on that. Chapter 2, that will be due on Monday. So please be aware, you've got to start submitting homeworks. And normally how I plan things are that I fix a day and almost all your homeworks are due on that day, but that is not possible in the summer course. So your homeworks are all scattered all over days. Sometimes they're due on Friday, sometimes they're due on Monday. There are places I can see where they're due on Tuesday, Wednesday, Thursday, every day. There is some homework due. So don't just think that homeworks will be due only on the weekend or only on Monday or only on Friday. They could be due any day. You got to be careful about that. I'll keep reminding you also. And that's basically because the summer course has, its dynamics are totally different. They're not the same as the usual semesters. All right, let's look at this problem. So what he's saying is asking you to determine the downward rotation angle of beam AB. If the average normal strain in cable BC is as given below. So you can see that if the rod AB is supported at A with a pin joint and at B with a little, maybe a metallic strip or a cord, I don't know, is not mentioned, but BC is a kind of a short link. cable. He says it's a cable BC. So BC is a cable, it is supporting the end B. But when you apply the load, downward load at B, which is shown there, that's the load you are applying right there. And when you, so kind of pulling B down, if you do that, what will happen to BC? The length of BC is going to increase. And that's what he's wanting you to find. Determine the downward rotation angle. He's actually asking you to determine if B takes a new position there somewhere, then what is the rotation angle? Let me draw this diagram for you here. So what's going on is you have this member AB. This is an A, this is an B, and let's say this is the longitudinal axis. And with the application of the load at this end, B moves down and it takes the new position will be something like this. This is the rotation angle theta, let's say we want to find. Determine the downward rotation angle of beam AB. What is causing this rotation? This rotation is caused by the downward load which is applied at end B. And the man has already given you the, so it is supported by this cable BC. And original length of BC is what? 1 meter. So this is the original length is 1 meter. And he has given that the normal strain in BC epsilon is given by 0.002, and the units could be millimeters per millimeter. In other words, in order to find theta, so let me name these. This is B, let's call this B prime. So I'm required to find theta, and I'm saying theta is approximately equal to tangent of theta, which will be equal to what? In this triangle, if you see what will be tangent of theta, it will be B prime divided by this length AB. That's the tangent of theta. And that's what we're required to find. So AB is known. AB is given as 3 meters. I know this. And to find tangent theta, then I'd need to find BB prime. Let's call this BB prime as delta L. If this is L, original length 1 meter. This is delta L, the change in length. Then my epsilon or normal strain is defined as delta L over L, which is given as 0.002. Therefore, what is delta L equal to? 0.002 times the original length L, which is 1 meter. So delta L is 0.002 meters. Everybody good? And so therefore now I got both. I got BB prime, I got AB, so I can find theta. Theta will therefore be equal to tangent theta, which is equal to, theta is approximately equal to, tangent theta is equal to 0.002 divided by 3 meters, which comes out to how much? 0.000667 is the, and what will be the units of this? This will be coming out in radians. And if you convert it, well, the answer is good enough in radians also, but because we don't have much of a physical feel for radians, I did convert it into degrees to see, to give you an idea how much is the rotation. And knowing that pi radian is equal to 180 degree, you can convert it into degrees, which come out to 0.382. Can you see what a small rotation it will be? Hardly visible to the naked eye, I'm sure, because degree by itself is a very small unit, 1 degree, and then this is 300th of that. So a very small rotation there, and that's the final answer. Any questions, anybody? Everybody good? All right. Let's move on then. I have now the second problem for you. There's the answer also. Here's problem number 2. Please read the problem. So you can see that there is a plate A, B, C, D. The original plate is there. If you see A, B, C, and D, that's the original shape of this. And then with the application of a shear force, determine the average normal strain along side AD. With the application of a shear force, when side AB was fixed, it adopts the new position A, B, C prime, D prime. That's the new shape. So if I want to find the strain in AD, how do I define strain in AD? That's what he's asking you to find. A, the average normal strain alongside AD. And then also the average shear strain in the plate. Note that line C prime and D prime remains horizontal. So this is exactly parallel to AB. All right, let's then draw the diagram first. In reality, I don't think I'm going to draw the whole diagram, but let's start with part A. The man is asking you to find normal strain in AD. How will you define normal strain in AD? It will be the change in length of AD divided by delta L in AD divided by the length of AD, right? And what is change in length of AD? It will be the final length minus the original length. And the final length is AD prime, and the original length is AD divided by the original length, which is AD. Everybody good? By the way, can you even see the top line I'm writing?
Yes.
Yes.
Yeah, we got you.
Good. So this is what we need to find. Do we know AD prime? No, we don't know. Do we know AD? Yes, we know AD. So, but we don't know AD prime. To find AD prime, what do I need to do? Well, I need to draw that triangle. Basically, this is what it comes out to. This is your A, this is your D prime, and this was your D, original AD. This length is given as 50 inches, I believe. Yeah. AD is equal to 50 inches. So in this formula, AD is known, it is 50 inches. And we want to find AD prime, which is this length. But this length is given, the vertical drop is given there, which is, you can see at the right, and he's shown this here, 0.2 inches. So if this is 0.2 inches, what is this length then? 49.8 inches. 50 minus 0.2. Everybody good? And what else is given now? Well, this is also given 0.1 inches. What is this dimension given 0.1 inch? It is this dimension. So this dimension is going to be equal to this dimension, right? Do you agree? So I know therefore that this is also given as 0.1 inch. This is 49.8 this side, and this side is 0.1 inch. Can I therefore find AD prime, which I need there? So AD prime is therefore equal to, by Pythagoras theorem, AD prime will be equal to the square root of 49.8 squared plus 0.1 inch squared. And when you do the math, it will come out to be approximately 49.8. But if you go to many decimal places, you can write it as 49.8001 inches. This is the new length AD prime. And by the way, this is going to be, so AD prime is smaller than AD. Therefore, when you put it in the formula, epsilon AD will be 49.8001 minus 50 divided by 50. So delta L over L, and this being larger, this will come out to be a negative number, and it will, the math shows me it came out to minus 0.004 inch per inch. That's the epsilon AD then, the strain inside AD. Everybody good? What's the next thing he wants us to find? This is part A done, the average normal strain alongside AD, and the next he wants you to find in part B, the average shear strain in the plate. So average shear strain in the plate would be what? In other words, we need to find this angle. Shear strain. And shear strain is defined as gamma is given by this angle basically. So if I call this angle gamma, then gamma is approximately equal to tangent of gamma, which will be equal to what? In this case, the tangent will be 0.1 divided by this side. So I will say gamma average is equal to the tangent of this angle, which is 0.1 divided by 49.8, which turns out to how many radians? 0.002 radians. That's the answer for the average shear strain in the plate. So normal strain inside AD and shear strain in the plate. Everybody good?
Yes.
All right, let's move on then. The next example is, and before I go to the next example, I have copied one of the, well, here are the answers for you. I have copied an example of normal strain from the example in your book 2.1. Exactly not the same as 2.1, but similar in a way, some way similar. What you are seeing in this is, for example, if you had two strings tied together like this, AB and AC, and then you applied a load here, what will happen to A? A will extend and come to this new position. Now, there will be strain in both the chords AB and AC. How will you define that strain? I'd like you to write it in your notebooks. What will be the normal strain in, for example, AB? So by definition, normal strain is the change in length over original length. Now here's the question, what is the change in length of AB? Is it A prime? Clearly that is not the change in length. The change in length will be A prime B, the new length, minus the original length AB. So please be aware, these definitions are critical, you have to understand. Sometimes the diagram may try to mislead you. Somebody might think that this is the delta given and delta over L will be the strain in AB. No, the strain in AB will be A prime B minus AB divided by AB, the original. And in fact, the next example I'm going to do with you is based on this kind of an arrangement. If you don't have a question, if anybody has a question on this, please speak up now. Otherwise, let's solve the next example. All right, let's do this example problem number 3. And what you see is that kind of arrangement in which you had cable AB and cable AC, and then you applied a load there, with the result that point A will move down. It will take a new position, A prime. And so the man wants you to determine the vertical drop in point A. He's actually asking you to determine this drop given what is he's already given to you is the average normal strain in both cables AB and AC is given as 0.002, so millimeters per millimeter. All right, let's solve this problem now. So what we have there is something like this. There is the fixed surface, and then I got that and that. And this is the new position. So when I apply the load there, this being point A, is it? Yeah, this is point A. And then I have a point B there, point C there. And by the application of a load here, this A adopts the new position, A prime. And what will happen to B and C? Well, you can see that B will become something like this. And similarly, C will become something like this. Maybe I should remove this. And the original dimensions given are, this is 0.3, this is 0.4. So what will be the original length of AB and BC? Obviously a 3, 4, 5 triangle, so this will be 0.5. So is this 0.5, the original length AB. So I can say AB is equal to AC is equal to 0.5 meters. 0.5 is not given, but you can easily find by using the triangle. So to be able to find this extension or the downward movement of point A we need to find what? In other words, we are trying to find this length, which let me say, since this is in the y direction, I'm just calling it y. Y is what we need to find, and what is given to us is the strain in either one of these. So I will say that if the original length is L, then L is equal to 0.5 meters. And let's say that the new length of AB is L prime, then L prime is equal to L plus delta L. And what is given to us is epsilon is equal to delta L over L. L we know, L is 0.5, epsilon is given 0.002, therefore we can find delta L from here. Therefore, delta L is equal to L times epsilon, which is 0.002 times 0.5, which comes out to 0. Let me write that whole thing, 0.002 times the length, which is 0.5, and this comes out to 0.501 meters. This is still L prime. We have not yet found Y. Remember, he's asking you to find Y. He's not asking you to find the new length. He's asking you to find Y. How do you find Y now? Well, if I know now let's see, look at the new triangle we have formed. Here is the new triangle, the dotted one. And in this L prime is 0.501. And this continues to be 0.3. So can I find this length from here? This will be this square minus this square under the root. In fact, this is, let's say if this was 0.5 and this was Y. Oh, sorry, this was 0.4. This is not 0.5. This original length was 0.4. And to that you add Y. Then I can say from this right triangle, can I say therefore 0 in triangle A prime CB. That's the triangle. I'm saying that Y plus 0.4 quantity squared plus 0.3 quantity squared should be equal to 0.501.
What was your delta L equal to again, sir? That 501?
Sorry? No, 501 was the new length, L prime.
Okay.
And delta L will be 0.001 because the original length of AB was 0.5. So 0.501 minus 0.5 will be 0.001. That's the delta L.
Where does that 501 meters come from? It looks like it's at 0.02 times 0.5, which would be 0.001.
Okay, yeah. This is delta L will be 0.001. So the new length will be L prime will be therefore L prime will be 0.5, which is the original length. This one 0.5 plus the change in length 0.001. So this will be 0.501. Correct. I should have written L prime as 0.501, not delta L as delta L is 0.001. I agree.
Gracias. Thank you.
All right. Thank you for the correction. And here is the from the right triangle, the new position of A prime. This was original position of A, and this is A prime, then that is my Y. And so now I have written Y plus 0.4 quantity squared plus 0.3 quantity squared should be equal to 0.501 quantity squared. And when you do that, you can find delta Y, it comes out to, or Y actually, not even delta Y, I'm calling it Y. Y came out to 0.001249 meters, or which is equal to 1.2493 millimeters. That's the final answer for Y. The change in length, the downward movement of point A. Everybody good? Let me see if I have another problem. Delta Y is 1.2493. All right. Here's a group problem solving. This is a problem from your book, textbook. You can solve it in your own time. Check the answers given in the book. It's similar to what we have done. And well, I put down the answers for you also here. So you can solve it in your time and check out your answers. Once again, you will note that for epsilon, I'm using the units, millimeters per millimeter. And that's what I expect you to be doing also. Always write the units of strain. Well, guess what? That's all we had to do in chapter 2. We've completed chapter 2 really. All I need you to do tonight is go over yellow pages 1 to 3, just 3 yellow pages in chapter 2. And then there are 2 homework problems for you. And no, these are homework problems from chapter 1. And then these are homework problems from chapter 2. 2-4, 2-9, 15, and 23. 4 problems from chapter 2, 2 problems from chapter 1 in homework number 2, which will be due on Monday. And the homework due tonight is from chapter 1.
A question for you, Professor. Those homework problems you have on a board, are those going to be collected?
No, they are the ones on mastering, and those are the ones you're required to solve.
Okay, I apologize.
No, thanks for the clarification. It's for the benefit of everybody.
Oh.
And any other questions?
Yes, Professor. I was doing the homework assignment last night, and the last problem, it seemed like there was some information that we hadn't gone over, or maybe I just missed it. It referenced resistance factors and dead load factors.
Yeah, I had the same question.
What's the question number?
I can
1.15. Example problems 1.15.
Let me see.
And I believe the last problem on our homework deals with the same thing.
Yes,
on
that's what I
mastering.
was thinking of.
You said example problem 1-15?
Yes.
Okay, let me read that. Supported by a steel rod and distributed loading of 3 kilonewtons per meter, determine the required diameter of the rod. The failure stress of the steel is use the LRFT method where the resistance factor for tension is phi is equal to 0.9. The load factors for the dead and live loads are, yes, you're right, we haven't gone over it, so delete this. I will delete this from your course.
All right. Yes, it's a problem 1.93 on the mastering engineering.
Okay,
Correct.
I'll delete that. All right, thank you for pointing out. 1.93, let me read the problem also. 8.4 is there, and then there is 9.3 there, okay. Use the LRFD method. Resistance factor for steel and tension is 5 and the dead load factor is, yeah, we haven't gone over it, so you can, I'm going to delete that. Thank you for pointing out. Any other questions or comments?
Yes, I had a question for, I know it's a little bit in advance, but for on the day of the test, are you going to be opening up the chat room early so that we could test our video setup? Because I know that it's required that we have our camera set up so that you can see us.
Yes, I am going to, I don't want to give extra time. What did you need the extra time for?
No. I mean at the beginning of before class begins, because since I'm working from home, I have my own little home office setup, and I do all my work on a dry erase board. So I wanted to make sure that I have my computer and my camera oriented in a certain way that's sufficient for you.
So I still don't understand what am I supposed to do in that.
I was just asking if you were going to open up this chat room a little bit before class begins, so that I could show you, so that you could see our camera setup and see if that would be okay or if we need to move it.
All right, I'll do that. Although your exam will still start at the hour,
Don't have a
which
problem with
means
that.
9:50. But yeah, I can open up earlier on.
Okay, thank you.
And I am going to give a poll the next time we meet on Monday, where I'm going to ask you if you have everything required for the test. That means you should have downloaded responders and you should have the camera set up with you, because these are the two things required for the exam. So this poll I'm going to do on Monday. I want everybody to have downloaded responders and everybody to have a camera set up so that the test can be observed. All right, any other questions or comments? Your exam is going to be on, well, the exam is on Friday, yeah, next Friday. So I will say that this was not this was a shorter class. We finished about 10 minutes early, appropriate to the Friday being the weekend. Have a nice weekend, everybody. I'll see you now on Monday.
What's going to be over the first test? Will it be just chapters 1 and 2?
It will be 1, 2, and 3 actually.
Oh, okay.
So we're going to do chapter 3 in the first 2 days of next week. You will still have 2-3 days.
Okay.
All right.
Thank you.
Welcome. Any other questions, comments? We still have time. I'm letting you go 4 minutes early. Keep that in my account. All right.
All right, thank you.
Good luck,
Thank you.
guys. Bye-bye.